Today we are going to discuss about the complete AI ML framework landscape, an enterprise architect guide in 2025 for MLOps to RAGOps navigating the modern AI infrastructure stack. Hi there. If you're responsible for AI infrastructure decision in your organization, the next 15 minutes will save you months of research and millions of dollars in potential mistakes. I'm going to walk you through the complete landscape of AI and ML framework in 2025, showing you exactly what works, what doesn't work. Let's start with a crisis that nobody's talking about. Right now, 70% of organizations are using cloud-based AI software, and 65% of ML workloads are running on Kubernetes. But here's the problem. Most teams still doesn't understand the full stack they are working with. The result? Massive waste, failed deployments, and vendor lock-ins that costing companies millions. And how to make the right architectural decision for your specific needs. Here's a stat that should make everyone. There's a 24x performance gap between different inference engine. That means your choice of framework isn't just a technical decision, it's a business critical decision that directly impacts your bottom line and your competitive advantage. The complexity of modern AI infrastructure has completely outpaced organizational understanding. We are deploying billion parameter models without understanding the architectural implications. We are choosing framework works based on what's trendy rather than what actually works for our use cases. And we are paying the price in failed projects and wasted resources. To understand where we are, we need to understand how we got here. Let me take you through the four phases of AI framework evolution. Phase 1, 2015 to 2018, TensorFlow versus PyTorch. Every data scientist had to pick a side, and organizations were making multi-year commitment based on these choices. Phase 2, 2019 to 2021, the deep learning explosion. Neural networks went mainstream, and suddenly everyone needed GPUs and distributed training capabilities. Phase 3, 2022, the LLM revolution. Foundation models like GPT-3 and GPT-4 completely transformed what was possible with AI. But they also introduced unprecedented infrastructure challenges. To 2023, Phase 4, 2024 to 2025, where we are right now. This is the multimodal orchestration era. We are no longer deploying single models. We are orchestrating complex AI ecosystem with multiple models, multiple frameworks, and multiple operational concerns. Here is the key insight. The framework wars are over. PyTorch won for research, TensorFlow is solid for production, and now the ops war has just begun. Your competitive advantage isn't about which framework you choose, it's about how well you operate it. Four pillars of modern AI frameworks. Now let's get into the architecture. Modern AI infrastructure rests on four pillars, and understanding these distinctions is critical for making the right choices. Pillar 1, machine learning frameworks. These are your traditional tools, TensorFlow, PyTorch, scikit-learn. They are designed for traditional ML and deep learning. The adoption pattern is clear. 80% of research uses PyTorch because of its dynamic computation graphs, while 60% of production system uses TensorFlow because of its mature ecosystem and deployment tools. Pillar 2, AI frameworks. These are broader platforms like Microsoft Bot Framework and IBM Watson. They are designed for hybrid AI solutions and design support systems, particularly in enterprise integration scenarios where you are combining AI with existing business systems. Pillar 3, generative AI framework. This is where things get interesting. Tools like LangChain, Llama Index, and ComfyUI are designed specifically for orchestrating content creation workflows. Here's a critical performance insight. ComfyUI is twice faster than alternatives for image generation. This performance difference matters at scale. Pillar 4, LLM frameworks. This is cutting edge. VLLM, Tensor RT LLM, and Hugging Face text generation inference. These are high performance inference engines, and this is where we see the 24 times throughput improvement I mentioned earlier. VLLM has become the de facto standard for production LLMs, serving for good reason. So how do you actually choose? Here is a practical decision matrix based on your use case. For research projects, go with PyTorch plus LangChain. Why? Dynamic computation graphs makes experimentation faster. The trade-off is that you will have limited serving options, but for research, that's acceptable. For production ML systems, TensorFlow Plus, AWS, Amazon Web Services provides the most mature ecosystem. You will face a steeper learning curve initially, but you will get battle-tested deployment patterns and enterprise support. For creative application, LangChain plus Confi UI gives you the best performance. You're trading some vendor specifics for the 2 times performance gain in generation speed. For real-time system where latency matters, VLLM plus TensorRT is your answer. You will achieve sub 50 millisecond latency, but you're accepting NVIDIA lock-in. At high scale, the trade-off is usually worth it. The key lesson: there is no single best framework. The right choice depends entirely on your specific requirements, your team expertise, and your operational maturity. Now let's talk about the elephant in the room: computational requirements and costs. Understanding the spectrum is critical for realistic planning and budgeting. Traditional machine learning sits on one end. You're running on CPUs, working with gigabyte to terabyte of data, training on hours to days, and spending hundreds to tens of thousands of dollars. This is accessible to almost any organization. Deep learning is in the middle. You need 8 to 32 gigabyte GPUs. You're working at terabyte scale. Training takes days to weeks, and cost ranges from $10,000 to $500,000. This requires serious infrastructure investment. Then we have large language models at the far end of the spectrum. Training Llama 3 required 16,000 H100 GPUs processing trillions of tokens. That's 4.6 terabyte of data over 54 days at a cost of $10 million to over $100 million. This represents a 1,000 times increase in computational requirements and cost from traditional ML to LLMs. You need to understand where your use case sits on the spectrum before making architectural decisions. Inside Llama 3 scale training, let me show you what it actually takes to train a modern large language model at scale. This is the reality behind those impressive capabilities we all use. The parallelism strategies are mind-blowing. First, data parallelism: distributed batches across thousands of GPUs simultaneously. Second, tensor parallelism: splitting individual layers across multiple GPUs. Third, pipeline parallelism: distributing different layers across different machines. Fourth, fully shard data parallelism, or FSDP, where even the model parameters are distributed across the cluster. Memory optimization is equally critical. You're using zero optimizer stage to reduce memory footprint, activation, recomputation to trade compute for memory, CPU and SSD offloading to handle temporary storage, and flash attention algorithm that provides 2 to 4 times speed up for attention mechanisms. The infrastructure requirements are staggering. Lustri or GPFS, distributed file system for high throughput data access, InfiniBand networking for ultra low latency GPU communication, processing 1.4 trillion tokens, and managing 4.6 terabyte of training data. This isn't science fiction. This is what Meta, Google, and OpenAI are actually building. Understanding this helps you make realistic decisions about whether to train your own models or use foundation models. Beyond SQL, the new data layer. Now let's talk about the revolution happening in the data layer. The traditional database stack is being completely reimagined for AI workload. Vector databases are now mandatory infrastructure. Tools like Pinecone, BV8, and pgvector enable semantic search across 100 million plus vectors. They are critical for RAG system and semantic search applications. If you are building any kind of knowledge retrieval system, you need vector database capabilities. Traditional plus vector hybrid gives you the best of both worlds. PostgreSQL with pgvector extension or MongoDB Atlas with vector search let you maintain a unified data model. This is ideal for applications that need both structured data and semantic search. GraphDBs like Neo4j and Amazon Neptune are essentially for knowledge graphs and reasoning applications. As we move towards more sophisticated AI systems that need to understand relationship, graph database becomes increasingly important. And don't forget specialized storages. Feature store like Feast and Tectone, time series database like InfluxDB, and analytics platforms like Snowflake all play a critical role in the modern AI data stack. The key insight: SQL alone is no longer sufficient for AI applications. You will need a multi database architecture. Why the vector database are now mandatory? Let me explain why vector database have become non-negotiable infrastructure. It all comes down to retrieval augmented generation, or RAG, which is transforming how AI system accesses and utilize knowledge. Here is the flow. A user submits a query. The query goes through an embedding model to convert text into a vector representation. Then you perform vector search against your knowledge base to find semantically similar content. The retrieved context gets injected into your LLM prompt. The LLM generates a response using the context. And finally, you return the answer to the user. This architecture solves the hallucination problem. Instead of relying on one model's training data, which might be outdated or incomplete, we are grounding response in your current accurate knowledge base. The performance numbers are impressive. Pinecone handles 10,000 queries per second with sub 10 milliseconds latency, scaling to 10 million plus vectors. VV8 provides 8,000 QPS with sub 15 milliseconds latency and unlimited scale. Even PG Vector, which is just a Postgres extension, handles 5,000 QPS with sub 20 milliseconds latency for up to 1 million vectors. The key technologies enabling this are HNSW and IVF, indexing algorithms. Now let's talk about cost optimization through performance engineering. This is how you make AI economically viable at scale, making AI affordable. First, quantify by reducing precision from 32-bit to 8-bit or 16-bit. You get 2 to 4 times speed up and 50 to 70% memory reduction. The trade-off: minimal accuracy loss, typically less than 1%. At scale, this is an absolute no-brainer. Second, model compression. Pruning can reduce model size by up to 90% while maintaining performance. Knowledge distillations let you transfer capabilities from large models to smaller, faster models. And Onyx Runtime provides cross-platform optimization that works everywhere. Choose the right servicing platform. Cloud options like SageMaker, Azure ML, and Vertex AI provide managed infrastructure. Open source options like TensorFlow Serving, TorchServe, and Kserve gives you more control. Performance varies widely. Databricks reports achieving 25,000 plus queries per second on optimized infrastructure. Here's the benchmark that matters. VLLM achieves 700 tokens per second with 100 concurrent users on a single A100 GPU. That's the performance target you should be measuring against. From MLOps to RAGOps, the operational landscape has evolved dramatically. Let me walk you through the 4th generation of AI operations. MLOps emerged from 2018 to 2022, focused on classical machine learning lifecycle management. Tools like MLflow, Kubeflow, and SageMaker became standard for model versioning and automated pipelines. This was about bringing DevOps practice to machine. AIOps appeared in 2019 and continues today. This is AI to IT operations, using machine learning to provide predictive insight and auto remediation. Tools like Splunk, Datadog, and Dynatrace apply AI to infrastructure monitoring and incident management. LLMOps emerged in 2022 with foundation model revolution. AWS Bedrock, LangChain, and weights and biases became essential for managing billion parameter training jobs and model benchmarking. This is about operationalizing foundation models at scale. Now, RAGOps is emerging as the newest discipline in 2024 and 2025. This is especially about retrieval augmented generation operations. Tools like Pinecone, Llama Index, and Azure AI Search are becoming standard. The focus is on vector database operations, prompt engineering, and evaluation frameworks. Each generation builds on the previous one. Mature organization needs capabilities built across all the 4 layers. The critical layer forms four foundation: data management and ingestion pipeline that keeps your knowledge base current, model serving and orchestration that handles LLM requests efficiently, and deployment automation that lets you iterate quickly. The essential layers provide operational excellence, prompt engineering and optimization to improve response quality, evaluation and monitoring frameworks to tackle performance, security and governance control to protect sensitive data, and caching strategies to reduce cost. The enhancement layers add advanced capabilities. Human in the loop workflows for quality assurance, cost optimization strategy for maximum efficiency, explainability and debugging tool to understand system behavior, and multi-model support for image, video, and other content types. Organizations that master RAGOps will have a significant competitive advantage in deploying production RAG systems. Let's compare the four deployment models and understand when to use each one. Infrastructure as a service gives you full control but highest complexity. Costs are variable. This is best for custom training and research work where you need maximum flexibility. Platform as a service provide medium control with medium complexity. Costs are more predictable. This is ideal for production ML and teams that want managed infrastructure without sacrificing too much control. Software as a service offer limited control with low Software as a service offers limited control with lowest complexity. You pay per usage. This is perfect for quick deployment and proof of concept where you want to minimize operation overhead. Function as a service provide low control with low complexity. Costs are event based. This works well for inference endpoint and microservices architecture. The cloud providers mapping matters. AWS offers EC2 P4D for IaaS, SageMaker for PaaS, Bedrock for SaaS, and Lambda for function as a service. Azure provides NC Series VM, Azure ML, OpenAI services, and functions. Google Cloud has GPU compute, Vertex AI, no native LLM SaaS, and cloud functions. When should you use infrastructure as a service? Four clear scenarios. When you need custom model architecture that managed service doesn't support, when you have specific GPU requirement like particular CUDA version or hardware configurations, when you are doing research and experimentation that requires maximum flexibility, or when you need full infrastructure control for compliance and security reasons. Your option spans cloud provider and specialized GPU cloud services. AWS EC2 P4D instance offer 8x NVIDIA A100 GPUs with high bandwidth networking. Azure NC series provide Tesla V100 GPUs with Azure integration. Google Cloud Compute offers TPU V4 integration for TensorFlow workloads. Specialized GPU clouds are increasingly attractive. Paperspace provides cost-effective H100 access for smaller teams. Lambda Lab offers GPU cluster on demand with simple pricing. CoreView provides Kubernetes native GPU infrastructure with excellent performance. Cost optimization strategies are critical. Reserve instances save 30 to 40%. Spot instances can save 60 to 90% if your workload can handle interruptions. On demand gives you full price but maximum flexibility for unpredictable workloads. Well-architected framework. Each major cloud provider offers comprehensive architecture framework aligned with enterprise best practices. AWS well-architected for ML includes six pillars: operational excellence, security, reliability, performance efficiency, cloud optimization, and sustainability. It covers six ML lifecycle phases and provides SageMaker-centric architecture guidance with comprehensive governance frameworks. Azure MLOps V2 focuses on four core components: data estate, ML lifecycle deployment, and monitoring. It integrates with AI Foundry and provides AKS native deployment patterns for containerized workload. Google Cloud Platform for AI ML perspective includes five pillars plus Vertex AI integration. There's special focus on TPU optimization for maximum performance and BigQuery ML native capabilities for data-centric workloads and workflows. The key insight: don't invent your own architecture from scratch. Start with this proven framework and adapt them to your very specific needs. They represent thousands of hours of field experience and best practices. Kubernetes for AI and ML. Here is the critical statistics. 65% of ML workload now runs on Kubernetes. Why? Multi-cloud portability, sophisticated resource optimization, and powerful auto-scaling capabilities. The specialized operator make Kubernetes practical for ML. Kubeflow provides an end-to-end ML platform for training, serving, and pipeline orchestration. TensorFlow and PyTorch operates enable distributed training across multiple nodes and GPUs. MPI operator supports high-performance computing for parallel processing workloads. Kaito offers automated LLM deployment and management, and NVIDIA GPU operator handles automated GPU resource management and driver installation. The technology stack spans 6 layers: application layer for ML workloads, serving layer for ML endpoints, training layer for distributed training jobs, storage layer for data and models, compute layer for GPU resources, and platform layer for Kubernetes itself. If you're serious about ML at scale, you need Kubernetes expertise on your team. Decision framework by organization size. Your architecture strategies should match your organization size and maturity. Startups with less than 50 people should use managed cloud services, go with SageMaker or Vertex AI plus OpenAI API, focus on speed to market and cost efficiency. Medium enterprise with 50 to 500 people benefit from hybrid cloud plus Kubernetes. Use open source MLOps tools combined with cloud PaaS services, focus on governance, security, and flexibility. With a slightly higher budget than a startup. Large enterprise with over 500 people need multi-cloud plus edge custom solutions. Deploy a full Kubernetes MLOps platform, ensure TOGAF alignment and comprehensive compliance. Can also consider a bigger budget compared to medium enterprise and startups. Don't try to build enterprise infrastructure if you are a startup, and don't use startup style managed services if you're an enterprise with complex compliance requirements. Match your architecture to your actual needs and capabilities. 2025 technology trends. Let me give you a preview of what's coming next in 2025 and beyond. Small language models are exploding. They are specialized model optimized for edge deployment with 90 to 95% cost reduction for specific tasks. They're domain focused rather than general purpose, and they're going to democratize AI deployment. Secondly, AI agent adoption is accelerating, and 57% of developers are now using tools like Olama. Multi-agent orchestration frameworks like Autogen and Crew AI are becoming standards. Autonomous workflows are moving from research to production. Third, multimodal architectures are becoming the norm. Instead of one large language model for everything, we are combining LLMs, small language models, and specialized models. This gives you optimal performance per task and cost-effective intelligence distribution. Fourthly, the modern AI stack is solidifying. Vector databases are becoming standard. Infrastructure orchestration frameworks are maturing rapidly. Safety guardrails are becoming mandatory, and domain-specific evaluation tools are emerging. My prediction would be Edge AI combined with agentic workflow will be 2025 breakthrough combination. Here's what defines real AI performance today. For LLMs, optimized inference engines like Tensor, RTLLM, and AVLLM are 20 times faster than standard transformers. For image generation, Compify UI doubles the speed, and the training at scale, Llama 3 sets the bar. These are the number that matters. Here is your AI infrastructure roadmap. The next quarter, audit, optimize, and prepare. Review your stack, evaluate vector databases, and cut inference costs. In 6 months, operationalize. Roll out MLOps, deploy RAG, containerize workload, and set up governance. In a year, scale and secure. Go multi-cloud, enable edge AI, and get compliant. This message is clear. Act now, because those who build strong AI foundation today will lead tomorrow. And that's wrap up on our AI ML EA framework in 2025. If you found this helpful, please do like, subscribe, and hit the bell icon. See you in the next one with insights and building the future AI. Thank you.